Round two. Ready? Fight. Okay, round two. Let's get more complicated now. So you'll notice a couple of differences. This was a weak sauce noob graph. The numbers were easy peasy. There were no units. There were no titles. It was a winner, winner, chicken dinner. This one, however, is a graph that you're more realistically going to see in this class. Notice that this represents speed in meters per second. And if it helps, you should probably write it as meters over second. And then the x-axis is time. Okay. From the previous problem, we should make some quick observations of what's going on. One, notice that each of these is partitioned in by fives, but every five you can see the graph lines will give you one. Okay. You'll notice that this is a positive slope, that this is a zero slope right here because it's flat line. There's another positive slope, and then at the end you have a total negative slope. So the math helps you get the answers, but the science also makes sure that you get the correct answer. So keep that in mind, okay? We haven't even read the problem yet, but we're analyzing the graph that we've been given. Identify the speed of the object at exactly 10 seconds. Exactly 10 seconds, exactly 10 seconds. What is happening at exactly 10 seconds? Well, here's 10 seconds. The speed that corresponds to that is 15. But don't forget your units. 15 watts. Watt? Meter per second. Okay. Part B, identify the time it takes for the object to be traveling at exactly 25 meters per second. So this time though, they gave you the speed and they want to know what the time is. If you want to pause and see you can figure this out without me, that'd be great. So pause. Okay, here we are at 25 meters per second. That only ever corresponds, in this case, to 30 seconds. Don't forget the seconds, the units, right? I gave you a question that was simple like that. Let me ask you another one, just for kicks. What if I asked you at what times was this person going 20 meters per second? Well, when you look at that, there's two cases where that happens, right? It happens at 25 seconds, and it also happens at whatever this is, 34 seconds. Okay, so you can have multiple representations. Just be aware of that. That was a what if. Part C, what happens between 10 and 20 seconds? This is a good question. What happens between 10 and 20 seconds? You're thinking, what do you mean what happens? I mean, well, we know the slope is zero, but does that mean it's moving? Is it not moving? Is it just sitting there and time is going by? Well, we have to look at the units, right? At 10 seconds, how fast was it going? It's going 15 meters per second. Let me ask you this. What was happening at 11 seconds? How fast was it going? Or at 12, or at 13, or at 14, or at 15? It was going how fast? And at 20, how fast was it still going? So from 10 to 20, it was still moving. It was moving at a constant speed. It was moving at a constant rate. Okay. This is like when you get in your car and you push the cruise control button, right? Whoever's driving pushes the cruise control button because it's a long trip. It's 70 miles per hour. You rev it up to 70, you push the cruise control button, and the vehicle stays at 70 miles per hour until you remove it. Okay, so that's what's happening here. It's not changing. It's not speeding up. It's not slowing down, right? So for example, this car, if we want to say a story about this car, it starts from rest in the garage, right? It speeds up to 15 meters per second. It stays like that for a while, and then it speeds up again to 25, all the way to, and then all of a sudden it starts to apply its brakes until it hits a stoplight and it's 0 meters per second again. Okay, it helps to conceptualize a story and give a story to these graphs so you understand them better. D, find the slope of the graph for the first 10 seconds. So for the first 10 seconds, it went 15 meters per second. It went 15, it increased by 15, right? From here to here, it increased by 15. And the time increased by 10. But look at those units. Look at those units. 15 meters per second over 10 seconds, right? What does that mean? Okay. 15 meters per second over 10 seconds. All right, check it out. How about we rewrite this as follows? This will help you out. 15 meters per second divided by 10 seconds. Right, because this is a complex fraction. This is division. So this is the numerator, goes right here. This is the denominator right there. And this is what I like to call KFC. I know your teachers taught you wrong. They said it was KCF, but it's not catchy. KFC is yeah. I tried Popeyes the other day for the first time, and at least here, I used to have Popeyes when I lived in Louisiana because it's legit over there. But I tried Popeyes the other day here in town, and it was like so overpriced and so whatever. So anyway, KFC is cheap enough. Okay, we put this over 1. You keep this the same. You flip this one around. 1 over 10 seconds. And you change the thingy thing. And when we do this, we notice that nothing cancels out diagonally. So if I multiply the top, I get 15 meters. On the bottom, I get 1 times 10 is 10. But I get s times s is seconds squared. Now, 15 divided by 10, we can give a decimal approximation for that, and it's going to be 1.5. So for D, the slope of the graph is 1.5 meters per second squared, which is pretty interesting because the units have been quite modified. But that's how it came out. That's what we spent so much time previously, doing the math and showing you how to do that. What do the units represent? This is a pivotal question. They represent 2 things. One, it represents the slope of this graph. Okay, so if I have a graph where the y-axis is in meters per second and the x-axis is in seconds, then the slope of that graph is going to be in meter per second squared because we divide. Okay, what does it represent in real life? Remember, this is speed and this is time. It represents acceleration. Acceleration is when you change speed, okay? When you're increasing, and in some cases decreasing. Okay, so there is a real life meaning to this math that we're doing. Unlike mathematics where you do word problems and they have no real meaning, right? Or you find the area of a trapezoid birthday cake, which nobody ever does. In physics, these things have real significance and real meaning. Okay. Find the area of the graph for the first 10 seconds and give the correct units. Oh, we got this. This is a triangle. I can do 2 triangles. The area of this thingy thing. Well, that's going to be 1/2 times base times height. That's going to be the base is 10, 1/2. Notice what I'm doing here. I'm writing the number with the units, seconds. By the way, I put a little tail on my s's. Otherwise, if I'm trying to be like you and writing this like really fast, look what that looks like, 105. Yeah. Remember, bad habits is what kills you. Okay. So I put a little s on a little tail on my s's so I know that it's an s and not a 5. And then the height's going to be from 0 to 15. but use the units. It's meter per second, right? The y-axis is going to be meter per second. Meter over seconds. I'm going to put this over 1. Look what happens to our units. The seconds cancel out because they're diagonal. We don't keep flip change because we're not dividing. These are all multiplications, okay, right here. So let's see. I get 10 times 15 is 150 divided by 2. That's going to be 75. And the seconds cancel out. I'm left with meters. Interesting. So for part F, the area of the graph is 75 meters. What do the units represent? Like if I told you 75 meters, what does that look like to you? What does that mean? What would you start doing? You would start measuring length. Okay, this is distance. So this is trivia. If I know how fast you're going and at what times you are doing that, I can tell you. I can tell you correctly if you were speeding, if you weren't speeding, if you were accelerating, if you were changing your speed, if you're slowing down, how far you traveled, all of these things. Uh, People do this stuff in real life, right? It's called highway patrol. So when they go ahead and visit a scene, they go ahead and measure skid marks, brake marks, where cars ended up, speed limit signs, all that kind of stuff. And they're able to go ahead and piece things together and find out exactly who done it, right? So in this case, the units represent, of course, the area of that region, but more importantly, it represents the distance that was traveled. Okay, very powerful stuff. If I wanted to calculate the total distance traveled by the object the entire 50 seconds, what would I do? If I wanted to find out the distance that this vehicle traveled in the whole 50 seconds, what would I do? And I hope you said what I hope you said, and that's you would find the area of this whole shape. Okay, so we showed you an example of finding the first 10. You would go ahead and split this up into a rectangle and then maybe another triangle and then a big triangle, right? Okay, and you would get all those areas, add them all up, and then you would know how far this vehicle traveled in these 50 seconds. Okay, so hopefully you wrote that down. That's very important. Don't leave it blank. What is happening in the last 20 seconds of the object's movement? So remember, let's think of the story, right? It made it to, these are the last 20 seconds right here, from 30 to 50. It made it to this top speed, but then at the end, it's going at 0 meters per second. So it's applying the brakes, it's slowing down. But you know from real life that if you start applying the brakes, you're still going to keep traveling, right? It's called a braking distance. And some vehicles have better braking distances than others, okay? I think one of the worst braking distances around for commercial vehicle is the Rolls-Royce, I think it's a Phantom. That thing is heavy and the brakes are bad. So from in the last 20 seconds, this vehicle had reached its top speed and it's slowing down. It's constantly slowing down at the same rate to a point where it's going to hit 0 and come to a full and complete stop. In the process of doing that, it is still traveling a bit. Okay. All right. Hopefully that helps. Peace out.